In this lesson, we are going to discuss geodesic deviation. This is another way to approach the concept of curvature. And in fact, it's probably the more important way of understanding curvature because it has an actual physical interpretation. So we've done this sort of round trip analysis, right, where we took a vector and we parallel transported it to another place and then parallel transported it to a third point. And then we took the same vector and we parallel transported it to the same third point going a different way around essentially a loop, and we compared the difference. Alternatively, by the way, we could have taken a vector and transported it here, then transported it here, and then back, and we could have compared the difference at the starting point, gone around a complete loop. Right? That's another way we could have done it. The point is when you do that, it's not completely clear what the physical meaning of all of that is. But geodesic deviation does not have that problem. We have an immediate physical interpretation of what it's going to mean. So we're actually going to harp on geodesic deviation for a couple reasons. One is we're going to discuss it in terms of its physical interpretation. We're going to use it to define the curvature. And when I say to define the curvature, what I mean is to define the Riemann curvature tensor, which is a 1-3 rank tensor that takes a one form and 3 vectors, right? That when we say we're going to define the curvature, we're really saying we're defining this tensor here. Now, as you already should know by now, this guy, we've already actually defined this. We've gone through that round trip method, so we know how to understand this in one context. But we know immediately that it can be attached to the connection, right? The connection on the manifold. Without a connection, the Riemann curvature tensor really doesn't make much sense. And the connection, of course, gets understood in terms of the metric, right? And so, just as a reminder, nature gives us the metric, right? That's what the theory of general relativity does. The metric gives us the connection. The connection tells us the curvature. But everything ultimately goes back to this guy, right? So we've lost a lot of contact with this guy because we'll talk about the connection plenty, but we'll never show you the formulas that attach the connection to the metric anymore. You just have to know they exist. Likewise, we're going to get to the point where we're going to talk about the curvature in a similar vein. You know it's attached to the connection. We've already shown the relationship, the connection, as it were, between the curvature tensor and the connection. But we don't talk about it anymore. So we're really thinking of things at a very high level in some sense. And every now and then we have to do a picture like this to remind us what the full story is. This is just a mathematical ladder that allows us to abstractify what's going on to greater and greater degrees. But we always have to remember that everything really depends on this guy, the metric. And below that, there's other things below this actually, right? There's the topology. Let's see. There's the topology of the manifold, right? Meaning, I guess what I should be saying is that we're dealing with a manifold, right? So the manifold is a topological construct, and the manifold itself is what owns the metric. So in some sense, I suppose we could say we're going all the way down into the manifold. But that's really not fair to say, because you can have a manifold without a metric. So our theory of general relativity starts with a 4-dimensional metric manifold where the metric is determined by the Einstein equation, right? 8 pi t mu nu, right? The Einstein equation, where we've kind of put this on hold for a little while. We're dealing with the vacuum for right now. Okay, so geodesic deviation, let's attack it. So when discussing this thing, you always ask, what method are we going to use to approach geodesic deviation? I'm going to use several. Today, I'm going to use the one that's found in the text by D'inverno. The book is Introducing Einstein's Relativity. It's a fine introduction. I don't know why I like this book so much, but I'm a big fan of this book. I think I'm looking always for something that's a little bit less intimidating than Meissner, Thorne, and Wheeler's book Gravitation, right? Which, as far as pedagogy of this subject goes, this book really kind of owns the field. It's a tremendously big book, and it's written, and the presentation of the text is very welcoming. On the other hand, it's a little bit deceptive because it's actually quite. You've got to be patient, right? You've got to really look through each and every element of its track 2 to really get a full benefit of the book. But we'll be doing both of these presentations. But today we're going to focus on the Diverno one, and I'll break it down as best I can. I'll go in a little more detail than the actual book. But since people often contact me saying, "Is there a good book I can go for this?" I'm not inventing anything here, right? I learned this from books, and I have my favorite expositions of these things, and I'm redoing my favorite expositions of them. I'm not inventing anything. In fact, it's funny because when we talk about the geodesic deviation, right, we're going to talk about a method of, looking at two geodesics, connecting them with a little bit of a vector, and then as we move down the geodesic, kind of seeing how this geodesic separates from this one as you move down the first geodesic. The first one we often call the fiducial geodesic. This is sort of the one we're going to use to mark off how others are accelerating or decelerating relative to it. But when I studied this, I was thinking, I have a great new way of expressing this, right? I'm going to show the connection between geodesic deviation and going around a curve and showing how they're actually ultimately kind of two ways of looking at the same thing. We've already done this going around a closed curve, although we kind of went around in two directions as opposed to going all the way around. Some books go all the way around. Some books go the way we did, this way and that way. I was going to show the relationship between that and geodesic deviation because I thought, that'd be clever. I'd be blending these two expositions. But then, of course, once I dug into Meissner, Thorne, and Wheeler's gravitation, he already thought of that. He already thought of that as a way of presenting. So even when I think I've come up with a new way of talking about these things, I dig into here and I find some, it's been thought of before. And that makes sense. This stuff's been around for 100 years. Some guy, some newbie in the field is not going to be inventing any new pedagogy. Okay, anyway, so that's the references. So the way the story of geodesic deviation begins is with a family of geodesics. And there I'm going to draw a first geodesic. I guess I'll give it a little arrow instead of dots because we're going to presume that it just sort of goes on forever. And this geodesic we're going to call the fiducial geodesic. The fiducial geodesic. Now that's, since I'm talking about pedagogy now, the word fiducial is usually found in Meissner, Thorne, and Wheeler. He likes to use this word a lot. No other book does, but it's very apropos, right? This is the geodesic by which we are going to measure all the other geodesics. And this geodesic will have a curve, gamma mu of tau. Tau is the parameter along the geodesic, and gamma mu are the coordinates. So as before, we're going to have gamma 0 of tau, gamma 1 of tau, gamma 2 of tau, gamma 3 of tau, and because this is a curve, we know that given any value of tau, I plug in, get these four numbers out, and that gives me the coordinates, x0, x1, x2, and x3 of any point along this curve. So that's a quick review of curves. I don't hesitate to review things that you should know by second nature because, you never know how long it's been since somebody's watched the last lecture. So this little refresher is not a problem for me. Now, what we're going to consider, though, is an additional geodesic, say right here, that kind of moves. The way I'm drawing it, I'm drawing it as though it's somewhat, in some sense, parallel, but it's not clear whether it's parallel or not. I could have another geodesic here that's not quite parallel to the first. We're not going to worry too much about what goes on down here or what goes on over here, but we're going to talk about how the geodesics are separating or converging. And that's what this analysis is going to be. So there's an infinite number of these potential geodesics, right? You could have one in here. I mean, there's as many, it fills space. The geodesic has to fill all of space. So we have to ask ourselves, if we're going to compare this geodesic with this geodesic, we have to have a way of identifying this geodesic or this geodesic separate from the fiducial geodesic. And the way we kind of do this, we could name each geodesic, right? I could call this one, say, delta mu of tau. I want to use the same parameter though. So if I choose a parameter, I get a point on this geodesic, I get a point on this geodesic, I get a point on that geodesic. So tau is going to be the same parameter for all of them. And then this geodesic up here, I could call, say, alpha mu of tau, right? So I could give each geodesic its own name. The problem, of course, is that there's an infinite number of them. So what I'm actually going to do is I'm going to create a single function that captures all of these geodesics together. Instead of tau, I'm going to create a function of two variables. In this case, it'll be gamma mu of tau and s, right? It's actually even more common, I think, to put the s first, s and tau, where s tells you which geodesic you're on. So this would be, say, the s equals 0 geodesic, our fiducial one. And this might be the s equals 1 geodesic. And then there's all these geodesics in between here that cover every real value between 0 and 1, and maybe all the way up here to the s equals 2 geodesic, right? So now I have a single function of two variables that can tell me for any value of tau and any selected geodesic s, the point in space-time that is corresponding to a certain value of tau and s. So this would be gamma 1 and, say, 0.05, right? That would be that point right there. Likewise, this would be gamma mu of 2.05, be right here. And this point here might be gamma mu of 0.05, right? And now I can imagine taking a line and connecting all the points of equal parameter value, like that, and then I create a new family of curves. And you might be tempted to say, oh, they're orthogonal or they're perpendicular, but none of that matters. It's just a family of curves that connect all of our geodesics by virtue of all having the same parameter value tau. That's why we're parameterizing all the geodesics with the same tau. They all have the same parameter value. So this one might be tau, whoops, that looks like a pi. Tau equals 0.5. And if this point here, say, was tau equals 1, then this might be tau equals 0.8. So I could have, so these red curves are identified as lines of constant tau, and each geodesic is a line of constant s. And there's a single function of two variables which describes this whole state of affairs. Now what we're interested in doing is trying to describe how, say, this geodesic here, where it's drawn a little more obvious, is diverging from this geodesic here. And the idea, going back to the basic fundamental principles of general relativity, is an object falling freely in space always follows a geodesic, right? So an object subject to no forces will follow through space-time a geodesic path. So by the way, this is a space-time path, right? So even though I'm drawing it as a line, in your head, you kind of got to think of it, you think of space as a plane. The path we're talking about is actually a line that kind of goes like this, where we have time on this axis, right? Actually, that would be not a good path, because that would look, depending on how I scale time. But if I get time in the same scale as space, then I should get a path that's time-like, right? Meaning I want it shallower than, I want this angle shallower than 45 degrees. If the rate of time is, if time is measured in meters and space is measured in meters, then this angle had better be less than 45 degrees for a real physical particle to maintain a time-like trajectory, which is required by special relativity. Anyway, the point is that when I draw this line here, for the purposes of this abstract analysis, you got to kind of remember, this is a line in space-time, right? It's got the time piece in it. And so it's okay to squash space in the two dimensions and then throw this line down. Of course, now that I have this line going this way, perhaps I should have drawn this picture like this, right? To give you a sense of space or time-like lines, because this kind of gives you a sense of, oh, it's space-like. But look, this is pretty abstract stuff. Just understand this is a line in space-time, which we presume for now is time-like. And you can use this picture to help you get there. But more importantly, if you thought about flat space, just regular old Lorentzian flat space from special relativity, you might realize, okay, well, geodesics are straight lines, right? When there's no gravity, when space is perfectly flat, objects move in straight lines. So here's our gamma, say 0 tau, right? Well, then a nearby point, you have this parallel line, right? And you could call that gamma of, say, 1 n tau, right? And those things would, in principle, move in perfectly parallel nature forever and ever. There's no gravity, so there's no reason those geodesics should ever converge or diverge. But I could easily have a different geodesic going through this point that looks like, say, this, right? And now suddenly those two geodesics are diverging, right? In other words, this green one, let me redo it in green. This green one is clearly diverging from our fiducial geodesic down here, and maybe this green one is actually gamma 1 of tau. I should have my little muse here for gamma. So what's to stop that from being the case? And if that's the case, I have a divergence of geodesics in flat spacetime. And the answer is that geodesic deviation is really looking for this distance, this change, this divergence, which we still have to quantify aggressively. We're interested in its acceleration. We're interested in the acceleration of that deviation, not just the pure deviation itself. We want to know about its acceleration. And clearly in this case, there's no accelerating deviation. So calling it geodesic deviation is a little bit alarming because it's not purely the deviation. It's not that the distance between the fiducial geodesic or an object falling along a fiducial geodesic and an object falling along a nearby geodesic. It's not that the distance is changing. The question is that change accelerating? Is it diverging? Meaning, is this deviation accelerating and getting bigger or accelerating and getting smaller? So that's the question we want to attack. Okay, so now we will redraw this, and here this black line is a given geodesic where we imagine holding s constant and running through all the values of tau. And this guy, same function, but now we hold tau constant and we run through all the different values of s. And from these two curves, we can derive two vector fields. The first one will be v mu partial mu, right? So this is the vector component and this is the basis vector in the coordinate basis. And that is, let me fix this mu. That is going to be d, or partial of gamma mu partial tau with the unit operator there. So this guy here is the value of v mu. So we could write simply the component v mu is partial of the curve with respect to tau. So, for example, v0 is the partial of the function gamma 0 with respect to tau. So a quick little review there. But we can also do this for the, that's because what we're doing with that partial derivative is, of course, we're holding s constant. We could do it the other way. We create z mu. Z mu is partial gamma mu partial s. Very frequently in textbooks, s is actually given as n. Also, by the way, I think n, the idea is some concept of normal vector, but you don't want to lean on the word normal, right? So we're using s. So these two vector fields are the tangent vector fields to these two curves. So, for example, at, say, this point right here, the tangent vector there will be v mu, which is a function of space-time, right? This is all going to be functions of space-time. And likewise, the tangent vector here will be z mu, right? So with those, we can now, and since there's a curve everywhere in space, right? You know, there's all these curves in between filling here for every value of tau, and all these curves filling in here. All this region of space-time is completely covered with these two vector fields. So there's a vector z and a vector v at every point in space-time. So these two guys are vector fields. Regarding them being functions of space-time, remember this here, well, I guess you need to think of it this way. This obviously is a function of these parameters s and t. Given s, given t, you get a location in space-time. That's what this thing is. You get gamma 0, gamma 1, gamma 2, gamma 3, and each of those are a coordinate in space-time. So given s and t, you get a coordinate in space-time. Likewise, if I take a coordinate in space-time, I can always find an s and t that identify that point. And at that point, I can calculate this vector, and I can calculate this vector, and therefore I have a vector field everywhere in space-time. All right, so let's take a look at what we have so far. We have the fiducial geodesic, which I'm drawing as a straight line now. We have a nearby geodesic, and then we have these connecting vectors. These are, I'm sorry, connecting curves. Now, the connecting curves at each of the points along the fiducial geodesic have a tangent vector, right? And we'll call that tangent vector z mu. And the fiducial geodesic at every point along it has its own tangent vector. And because I've drawn it as a straight line, it just so happens the tangent vector looks like it's right on the line. So ultimately, the question that I want to ask is, how is this vector here, as I move along this line in space-time, how is this vector here changing? And to get at that question, we have to remind ourselves of the notion of the absolute derivative. The absolute derivative, the absolute derivative of any tensor field t. In this case, we're interested in z, right, the vector field z, but it could be any tensor field. We could ask, what is the absolute derivative of a tensor field as you move along some curve in space? And the definition of that thing, we write capital D, capital, and tau, where tau is the parameterization of our curve, of our fiducial geodesic. Well, I guess the way we're doing it, I should write it this way. Gamma of 0 tau, like that, right? So with that in mind, t is a function, of course, of space-time. So I'm asking, what is this absolute derivative of t as we go along, as we increment the parameterization of the fiducial geodesic? So that's this. So these vectors z, the ones I've actually drawn, they're different from one another. And of course, all of this involves parallel transport, just like before. And that definition is the covariant derivative in the direction v of t, where v is the tangent vector of the curve you're interested in. And that is v alpha, covariant derivative alpha t, which is also written as v alpha t, and then t has a bunch of indices, whatever they are, but I double bar and put alpha there, right? T is some tensor, right? So it should, if I'm going to go into coordinate notation, I need to put its upper and lower indices into position. In our circumstance, the one we're interested in is or one of the things we're interested in is the absolute derivative of z mu d tau, which is going to be this guy, mu. Actually, I guess I have to keep this abstract, right? If I'm going to start abstract, I got to keep it abstract. So then that can be written as V alpha partial alpha Z mu, Z mu, which is V alpha Z mu double line alpha. Okay, that's the absolute derivative. But as we already said, the absolute derivative, what that's expressing to us is it's telling us how this, essentially this approximation to the connection, right? This little piece here is sort of an approximation to a connecting vector. It's how is that changing as you move down this curve? And we already know that even in flat space, you can have divergences in flat space. So the fact that dt d tau is not zero, that's not important. What's important is d squared z d tau squared, which is partial v, which is covariant derivative in the direction v twice of z, which is going to ultimately be v alpha v beta z mu double bar alpha beta. That's the guy we care about, because that represents the acceleration of this vector as you move along here. And we'll see this guy come up again in a moment. So it is worth noting that the commutator between the vector field of tangency along the geodesics and this connecting vector field, that commutator equals 0. It's not too hard to understand why that would be. They're both defined through the same function, right? This gamma mu of s and tau. That's a function of two variables. And we're going to see that because it's a function of two variables, that ultimately this ends up being the commutator of two partial derivatives in different orders, which is 0. But I can show that. It's kind of a worthwhile exercise to review. But I replace these two abstract coordinate-free vectors with their coordinate basis interpretation. And then I replace v mu partial mu with what is the definition of the tangency to a curve. Well, if the curve is given by gamma and v is defined as, s held constant, then it's the partial derivative of gamma mu with respect to tau. That's what v mu is. This partial derivative with mu is with respect to gamma mu. So, because remember, in a lot of our curve is gamma mu of s and t, which is gamma 0, gamma 1, gamma 2, and gamma 3 at the point st. So this is x0, x1, x2, and x3. So we've basically replaced our coordinates xx with gamma. So we could have defined our curve as x mu of s and t, and many, if not most, books actually do. But we've gone with gamma, so we end up with our coordinate system sort of replaced by gamma. So, so this becomes this guy, and then this part here is gamma nu with respect to s, because this is the connecting vector, which is tau held constant, and then it's got its basis vector. And then we reverse the two over here. Now what I want to do is I want to take these guys, these last two terms here, the last factor as I've drawn is a differential operator. Here we have a differential operator, and here is a differential operator, and here's a differential operator, and here's one. But just by changing this nu to a mu, then this differential operator will be the same as that one. And I can do that because it's a dummy index. So if I change that to mu, then of course I have some ambiguity because this could be the summation. So I can't have the same dummy index in the same term. So if I change this to mu, I have to change that to something else. So I'm going to change that to delta, these two mu's to delta, and this dummy pairing will become delta, and this dummy pairing will become mu. And that's what I've done here. That dummy pairing is delta, and then I have mu. This guy was a mu, but I pulled it out because it matches this guy. So I pulled out the mu. And that makes sense because the commutator of two vectors is another vector, and there's the basis for that other vector. So now I have to kind of work on this thing. So to do that, I'm going to take this guy, partial with respect to gamma delta, and I'm going to write it as the partial of the parameter tau with respect to gamma delta times the partial with respect to tau. It's a simple chain rule. Remember, gamma delta is a function of tau, right? So I can clearly do this. This is just a simple chain rule. And when I make that substitution, what do I get? And this is what I get. This guy here gets replaced by that there. So this is the this differential operator is identical to this differential operator. It's just the derivative is being taken with respect to tau and as opposed to respect to gamma x1. And then I made the same change here for partial with respect to gamma mu. I made it with respect to, oops, I'm missing a partial derivative here. It should be a partial s. And, well, the good news about this is that this cancels to 1. Right? That equals 1 and that equals 1. And that just leaves me with the second derivative of gamma mu with respect to tau first and s second minus the second derivative of gamma mu with respect to s first and tau second. But gamma mu is a function of s and tau, right? So we know that partial derivatives, normal partial derivatives commute, so that equals 0. So that proves this assertion. And that'll be useful to us in a moment. So now we're going to go back to the definition of the Riemann tensor that we've already learned in a couple lectures ago. This is when we define the Riemann tensor as a rank 1, 3 tensor that takes one covector and 3 vectors. And its definition was the dual space mapping between that first covector and another vector that's formed through this thing called the curvature acting on C. So notice the ordering this is pretty standard, right? A, B lands inside this curvature object, and then C is acted on by the curvature object. But ultimately, this is a vector. And I gave you this by sort of postulate. I said, this is how we're going to define the curvature. And I provided the definition. Well, I guess I should write it out. And this is what you get when you write it out. You get these covariant derivatives in sequence applied to the vector C minus the opposite sequence applied in the direction C minus the covariant derivative of the vector defined by the commutator of A and B in the on C. So remember, that guy here, the commutator of two vectors is a vector, so you can take the covariant derivative in the direction of whatever that vector is of C. But ultimately, this guy here is going to be a vector. And then you apply it to omega, and you get a real number. Now, the next thing we're going to consider, though, is we're going to leave this omega out of it. Right? We're going to leave the omega out and just leave it blank. Which means what we have left is a 1-3 tensor that's waiting for, that was given 3 vectors, but no covector. So it is an object waiting for a covector, and it's an object waiting for a covector, but will give you a real number once it gets a covector. Well, what kind of object waits for a covector to give you a real number? Well, that object is a vector. So this guy here, as written with this spot blank, is a vector. So it's an object that takes 3 vectors and returns a vector. And that object's defined this way. So we're going to now apply this object to our vectors. We're going to set C equal to V. We're going to set A equal to V, and we're going to set B equal to Z. I got to be careful because Denverno and Meissner, Thorne, and Wheeler actually do it in opposite ways. I think Meissner, Thorne, and Wheeler go V, Z, V, and they end up with a minus sign different in their final equation. But regardless, let's do that. And this is what we get. We're basically making the replacement. A goes to V, B goes to Z, and C goes to V. And we end up with this guy right here. And so that's this curvature tensor applied to our newly created vectors that are special, right? This is a special application because V is the tangent field to a geodesic, a family of geodesic curves, and Z is a specific connecting vector that connects those geodesic curves together. And we know some things about them. For example, we know that for any geodesic curve, if the tangency of the geodesic curve is V, we know that the covariant derivative in the direction of the tangency has to be zero by definition. That's how we defined geodesic curves. So given that, we can immediately say this term is zero. And because of the way these curves were constructed between V and Z, I already showed you that the commutator was zero. So this guy here is zero, therefore this guy is zero, because the covariant derivative in the direction of the zero vector is always going to be zero. And that leaves us with this final expression that's only true for the particular vectors we've chosen. This is not in any way to be understood as a definition of the curvature tensor. The curvature tensor's definition is this. And remember about the commutation of two vector fields. This is telling us that S and T could be coordinates, right? Because their associated vector fields commute, right? This forms a holonomic basis. You can locate every point in space-time unambiguously with an S and a T. That's sort of what this commutator here is telling us, and that's kind of interesting. But it makes perfect sense by the way we constructed everything. But this is only for this particular vector field, because in general, vector fields do not commute. But in this particular case, they do. And certainly in general, the covariant derivative of an arbitrary curve through space-time, right? You take the tangent vector and you move it along an arbitrary curve. It's not going to be dragged into itself for an arbitrary curve. Only for a geodesic is it dragged into itself. So that explains why this resolves in this way for this particular case. For this particular case, we can write this down. All right, so now I need to show an intermediate result that gets kind of blown through in Deverneau's presentation. But let's go back to it's a good chance to review the covariant derivative, right? The covariant derivative of x, now I'm writing it in this notation. I could certainly have done it this way, x beta double bar alpha, right? The covariant derivative with respect to a vector of a vector is given in definition. By definition, it's the regular derivative of that vector, and then it's got this connection piece where the vector is summed into this first index on the connection. And that's the whole thing that drives the notion of parallelism and allows us to create geodesics. And the covariant derivative is a majorly important construct, not only in general relativity, but also in field theory, where it shows up in the context of what's known as gauge, as basically gauge transformations. But that aside, that if we consider that our definition of the Lie derivative of the component of a vector field, in this case the mu component of a vector field in the direction of another vector field A, was given by this expression, which was simply the commutator of A and B, and I guess since the commutator is a vector, this has to be the muth component of that vector, right? So this Lie derivative is given by this expression. But what's important to note is, imagine if we took these partial derivatives and just replaced them with covariant derivatives. What would happen if we just did that arbitrarily? Well, what would happen is I would take this guy here and replace it with this, which mimics this structure up here. And I would take this guy here and replace it with that, right? And then I would take the difference. That's this minus sign comes from here. So it's this minus this is now this minus this, with the only difference that the partial derivatives, the straight partials, are replaced by covariant derivatives. And if I do that and I break this open, this part and this part reproduce this. So I get that. And then this part minus this part gives me this thing here, which is the connection where delta is summed into beta, alpha is summed into A, and delta is summed into A and alpha is summed into beta, and I'm subtracting those two. But in general relativity, where we have a torsion equal to 0, you remember our lecture on torsion, I know that the connection is symmetric in those two indices. So this term goes away. And what this tells me is that everywhere I see a Lie derivative, I can arbitrarily swap out in a general relativity universe where the torsion is assumed to equal to 0. I can arbitrarily swap out this covariant derivative. And the reason that's important is because I know that the commutator of V and Z, I guess I should draw it again, the commutator of V and Z, that equals 0. So now I can actually write that what that's telling me is that the partial derivative in the direction of V acting on Z minus the covariant derivative in the direction Z acting on V, that equals 0. Right? Because this is defined in terms of just partial derivative operators, but I can arbitrarily swap out these covariant derivatives for them because of this property here in the torsion-free universe. So Duverno just sort of lays that down there, and I think it's a bit of a jump. It's a little bit more than elementary what he goes at there, but it is what he says. And the reason that this is important is now I can write the partial derivative of V, I keep saying the covariant derivative in the direction V of Z equals the covariant derivative in the direction Z of V. And then I take the covariant derivative of both sides with respect to V. So I can write now the covariant derivative in the direction V of the covariant derivative in the direction V of Z equals the covariant derivative in the direction V of the covariant derivative in the direction Z of V, right? And then if I get rid of the brackets, which were only there to make it clear what was going on, I end up with this expression here, which tells me that this guy, the covariant derivative in the direction V of the covariant derivative in the direction Z of V, which is this, is actually equal to this. So now I can write direction V of Z. Okay, so let's put that in a summary line. There we have that as our new starting point. And now we're going to remember what this guy is. That guy is equal to the second absolute derivative with respect to tau, which is motion along the geodesic. That's what this side is. No, I better be a little careful here. Hold on. I better move that like that. And I guess what I should do to make sure that that equality is logical, right? It's still a dual space mapping, right? So we're fully expecting this to be a vector, and it is. It's the acceleration of something. Acceleration is a vector. This guy's a vector waiting for a covector. But this is the definition of this. I kind of went through that a few slides ago. And so that is our geodesic deviation, right? That is our geodesic deviation. So now if I put all of this into a coordinate basis, and I write this in the coordinate basis, and I write this in the coordinate basis, what will I end up with? And I'll get this object. Now notice this guy here is the components of a vector, because that sums, and that sums. The delta, gamma, and beta indices all sum out. That represents inserting these vectors into that slot, and I'm left over with a contravariant index, which is the component of a vector. So this guy would now have to have a partial alpha out here if I was going to include that vector, which most books don't, as I've said often in my lecture series. Then this over here is just our representation of that acceleration, which is a vector as well. So now I know that, and the way we ultimately write this is d squared of the connecting vector z d tau squared equals minus, minus r alpha beta gamma delta v beta v gamma z delta equals 0. Now, like I said, some books will have a plus sign here, and these two are switched, meaning that we have an anti-symmetry in these last two indices, and it really kind of depends what you order these guys. If you go V, Z, V, for example, you end up with a different sign. But the way DeVerno does it is the way I've just done it here. So that is our final expression for, undo. That is our final expression for the equation of geodesic deviation. So in the next lecture, we're going to dig into this a little deeper and take the Meissner, Thorne, and Wheeler approach. Because as it stands right now, this all looks very clever. This we can interpret right away as a literal acceleration, right? Z mu is measured in meters, right? This is, well, I guess I should put, this we can interpret as, we interpret this as proper time, and we can interpret this as a connecting vector, and this would be meters per proper time squared, so that's an acceleration. And an acceleration is given by some property of the space-time through the Riemann tensor, which distills itself all the way back to the metric, because the metric gives us the connection gives us the Riemann tensor. You know, we could also say the metric gives us the Riemann tensor. We can write an equation for the Riemann tensor in terms of the metric. It's not a big deal. It's second derivatives of the metric. But ultimately, the metric, the nature of spacetime itself gives us this, and that will tell us how these geodesics separate. And for example, if I want the acceleration in the z direction, or in the the z direction, be d z3 d tau squared, right? And then that would be, that acceleration is going to be equal to r3, and then beta gamma delta summed over v beta v gamma z delta. I do need to know what geodesics we're talking about, right? I need to know the geodesic path we're talking about, and I need to have constructed this. So I definitely need to know this, right? That, which is basically me setting up the situation of the problem. But this is an acceleration. So obviously we're going to be able to think of that as a force, mass times acceleration, right? And this guy here times mass would be interpretable as some sort of force. And that is how we would think of it in a Newtonian sense, where this ends up sort of manifesting itself as a force. So in the next lecture, we're going to kind of go through that exercise, the Newtonian comparison with the geometric or Einsteinian version of things. And also, I hope next time to have a chance to motivate this here, to motivate this definition, which we applied a couple lectures ago. I don't think it's easy to motivate it at the beginning and then present it logically through. I think it's easier to present it and then motivate it at the end. The reason is not clear to me, but most books that I work with actually do just sort of present it, and most of them don't even try to motivate it. But Meissner, Thorne, and Wheeler does, and I think we'll follow his exposition. I keep saying his, but it's three guys, right? Meissner, Thorne, or Wheeler, whoever wrote this section. We'll try to figure out their exposition and come up with the motive for this expression. And once we have the motive for that, everything will come into place. But ultimately, this space-time curvature does tell us what we want. It talks about acceleration of free-falling objects driven by the nature of space-time. So this is very plausible. This is a very plausible explanation. Okay, so I'll see you next time.